H2, okay, and sorry, not this, I'm sorry, H2 and sulfur dioxide, these two, coming out with sulfuric acid. So now what do you do with the sulfuric acid? Well, you got to close the loop so you have no waste, okay? So this is a chemical cycle. You put the sulfuric acid, you vaporize it, add heat to it at 800 C, and you can thermally dissociate it. You don't need 2000 C, 800 C. We have 880, so more than enough to dissociate in sulfur dioxide. Water, you put this back, and you get the electrolysis. So this part splits off the oxygen, this part splits off the hydrogen. You say, well, how much energy do I need here? Naively, you would think it needs 87% energy is conserved, right? So whatever you need to split water, if it's 13% of the electricity up there, which we get it from things that are not very useful, this intermittent electricity from solar and wind. So that's how we help them. That's a storage, chemical storage. You would say, well, it must be 87%. That's not quite right. And this is why we need chemical engineers to tell us, no, Frank, that's not quite right. Okay? Why is it not quite right? It's because this temperature is not that same as that temperature. dG, the change in the Gibbs free energy, is the change in internal energy. If this were all there was, it would be right. But it's plus V dP and minus S dt. And although these may be carried out isothermally, there's a change in temperature from going there to there. And that means it's a loss of useful energy when you do that. That useful energy is something none of us were taught, and we should be shot for it, because it's a very useful concept that Gibbs called exergy. Okay? When you have chemical reactions that have, or any other kind of things that have changes in temperature, so you lose a little bit of the energy that you would have been able to use if all you were dealing with is isothermal or isobaric processes. So that's called loss of energy. So it's not quite 87%, it's more. But if this is cheap, I don't care it's more. Okay, so what? 95%, 100%. If nuclear energy is very cheap, and as I said, it's 1,000,000 times cheaper than any form of fossil fuels or other energy, you can do it and still be viable. So what can you do? Well, hydrogen plus carbon, you can make hydrocarbons. So everything that can be done with fossil fuels, if I have coal, I can take, once I have hydrogen, make all the oil that you want. Okay? Do we know this for a fact? Yes, Germany did it. In World War II, all they had was coal, but to run tanks, you need oil, and they made coal into oil. Okay? You have to have a source of hydrogen. What do you do with the oxygen? Well, you can burn the coal, especially if it's a renewable coal, we call it biocoal, from renewable plants. You can burn it and get pure carbon dioxide. If you burn it with air, you have mostly nitrogen. If you want to sequester that, you can't, because 5 parts of it is, compared to 1 is nitrogen. So that's too expensive. So that's why people talk about carbon capture. First, you got to capture the carbon dioxide, separate it from the nitrogen, get out the water, and then go bury it. That costs money. But if you burn it with oxygen, that is a byproduct of this. You get carbon dioxide, you can directly reject. Now it only adds 10% to the cost. And now you've sequestered the carbon dioxide, you go negative, because every year you can grow more biomass to make the bio. So that's a complete game changer. When you have negative sources of carbon, the more you use, the better the climate gets. The more you use, the better the climate gets. That's what we want to do. Okay? Okay, so what's the design? Well, the design is pipes plus a big pool. I'll just draw this graphically. You have lots of pipes. They sort of look like conventional reactors, except it's in a big pool of molten salt. And in between, we want to build a spherical reactor. Why? Because I want to make this look most like a star, right? So it's a sphere. But you say, that's crazy. How can you build a spherical reactor? The first reactor that was ever built by Fermi was a spherical reactor. He built it in a squash court. How difficult is that? He did it in 6 weeks, knowing nothing. It's not difficult, okay? He built half a sphere, okay? Because he had a reflector. But build a sphere. Why a sphere? Because a sphere has the least surface area for a given volume. So it needs the least, has the least amount of losses at the surface. So you need the least fuel to do that. So how do you define that sphere? Well, it's wherever the moderators are. The pipes have very little carbon. In between, we're going to put lots of little carbon balls in here and let them float in the thing. When we've got enough, we stop filling a given channel, okay? So it's completely scalable. It's modular in the sense, if you want a bigger reactor, put in more pipe, build a bigger pool. If you want a softer spectrum, put in more carbon between it. And that carbon is pretty cheap, all right? It's just balls of graphite. Now you have fuel running, let's say, from the top down the bottom to be collected in these fuel salt channels. And they're having nuclear reactions when they enter this region. So they're giving energies to the wall transfers that energy to the blanket salt, which is at 88 DC, and you use that to do whatever you want to do. This kind of heat exchange is called a tube and shell heat exchanger. And it is known by chemical engineers to be the most efficient design to transfer heat that's released in the fuel salt to heat that you put into the blanket salt. Okay? So what temperature should you run it at? Well, the pumps control that. Okay? How hard you pump it, as we'll see, controls the temperature that you want to run it and how much energy you get out. Okay, in addition to this, the reaction energy, there's always decay heat. There's fission products are still radioactive, many of them, and they add decay heat. And that decay heat is the only reason that nuclear reactors can have accidents. Okay? All the nuclear accidents that have ever taken place is not because you couldn't stop the reaction, which is easy. It's that after you stop the reaction, there's still decay heat. And now you've got to run pumps to cool the decay heat. And what happened at Fukushima was they were running finally down to chemical pumps, chemical batteries, running pumps. After a few hours, those were gone. And then we had one explosion after the other. Okay? So you got to not run out of electricity, all right? And you got to keep running for 1+1 pumps. So what's the best way to do this? The best way, if you think about it enough, is to use the decay heat. Can you use the decay heat and turn it into electricity? Then it solved itself. And we can see that that is possible, may be possible. Okay, I think I'm running close. I won't go through this too much. You need to do neutron transport. It's like radiative transport, but harder. It's also like stellar dynamics, but harder, but not much harder. So let me tell you what is our way of doing neutron transport, the basic ideas. The neutrons are scattering off nuclei that are 9 times heavier than beryllium. 9 or carbon 12 mostly, or fluorine, which is 19, or sodium, which is 23. So each collision, actually, if it's going at a certain speed, you can only lose a small fraction of the speed. So the changes of its speed is just small. Okay? That means you have instead of solving the full Boltzmann equation, you can solve a simplification of it, which is called the Fokker-Planck equation. You expand in small changes of the speed and small changes of the speed correlation, delta V. And it's small compared to V. You get a Fokker-Planck equation, which is what Fokker and Planck did to explain Brownian motion that Einstein talked about, but which has now been adapted in many other fields Chandrasekhar used it in dynamics of globular clusters. Roger Blanford used it in cosmic ray acceleration. I understand he gave a talk about this. So when I told Roger about what this was, he immediately understood, okay? It's really a huge pleasure to talk to somebody so smart. Or, in economics, it's called the Black-Scholes stock pricing. I should briefly explain this. These things from physics can be calculated from physics principles. Yes, if you say delta V is the price, and delta V is the fluctuations in the price, how can that be calculated from physical principle? It must be calculated from economics. Economics is not physics. So they must have some assumption. They call it a postulate, but it's an assumption. That assumption is called that of the perfect market. The market always prices things perfectly. If that's true, then you can calculate those two coefficients, what it was 1 millisecond ago. The next millisecond you trade on that basis, and make money, a tiny amount of money, but over a long time you can learn lots of money. That's what's done. That's why Wall Street comes to astronomy departments, physics departments, to recruit people so they can do this quickly. Is this really true that they've removed risk from investing? No, it's not true. Is this hypothesis correct? Most of the time, it's about right. Okay. Next millisecond is not that different. But occasionally, there's a black swan event where there's a huge fluctuation and it brings the whole world economy down. That's what happened in 2008. So if you learn this stuff, you can do all those things, but I hope you won't do this. Even though these guys won the Nobel Prize, it's not a good thing to do, okay? Just like climate change. 1 degree, 2 degrees, it's not going to kill you, but a huge fluctuation that produces a superstorm, that could kill you. Okay, those black swan events are the ones that kill people and kill economies. So we have, on the face of it, a mess. It's 7 partial differential equation with coefficients that involve integrals of the distribution function. How can you solve such a thing? Well, do it step by step. First of all, the space part, you have to realize that when you have neutrons moving in solid or liquid matter, the mean-free path is actually quite small, even though it's only nuclear cross-section. It's only about 1 centimeter. These reactors are meters in size. So that's small compared to mean-free path. It means basically in configuration space, it's doing diffusion. Okay, and we know how to solve diffusion equations. Moreover, the equations, although they're partial differential equations, are quasi-linear. They look linear, but actually they depend on integrals over the distribution function. But nonetheless, they look linear, and the distribution function is almost isotropic. So instead of being 3 space variables and 3 velocity variables, there's actually only radius if I have spherical symmetry, and energy, you can try separating them. Okay? Separate variables. What should you use for the spatial part? Well, you should use the 0th order spherical Bessel function. All of those of you who do interferometry should know that's sine kr over kr, where k is some constant that's to be determined. How do you find it? It's an eigenvalue, which you use to satisfy boundary conditions. That's between the core and the pool, okay? So you get that. And then the rest of it, you can solve, almost solve. You get a 2nd order differential equation, not that easy to solve, but there's a big parameter in the problem. When you take product of 2 things, compared with the product expectation, what have you, of it by itself squared, that's a big number typically, because the fluctuations aren't always in phase. Usually lots of them out are phase. So that's a large number. And whenever you have a large number, okay, you should see if you can use asymptotics. Okay? That's what I made my career at, okay, at the knees of C.C. Lin, okay? So I could do this problem analytically. what it takes supercomputers 4 months to do, I can do, because I'm not a good programmer, one day on this Mac and plot it up. And my dream is to make an app out of it, so kids, instead of playing computer games, will design molten salt breeder reactors to make it really transparent how easy this stuff is. Okay? So you do it. Here's the distribution function. It's completely analytic. Okay? It's a complicated function. But it's really in 2 pieces that I could do it. I couldn't do it exactly. What happens is when you emit the neutrons, it's an amazing thing. There are 224 nucleons vibrating, and it's spitting out neutrons. What should this spectrum look like? If you guess, you say, right, Maxwell, yeah. Right! That's what Hawking guessed, and that's the right answer here too.